pictures of it over there. That way we don't have each other anymore.
Gotta do it after class.
Okay, let's do it after class because we're. Okay. Okay, so how is the homework assignment going?
It's hard.
This is the first one. And I intentionally chose some tricky questions, but they shouldn't be too hard. The difficult chapter is the next chapter because you're going to have multiple terms that sound exactly the same. Electric field, electric potential energy, electric something else. You're going to get confused very easily. So we have to find a way to prevent that. And probably the best way is you just make notes when you're reading the chapter. So, are there any homework questions that you want today to talk about today? Okay, you're going to tell me later on. Now, let me quickly summarize where we stand so far. We almost finished the chapter. We just have to talk a little bit more about Gauss's law. So we started with the standard experimental observation of existence of electric charges by looking at the attractive forces or repulsive forces that appear after rubbing a piece of material. After that, we talked about the fact that electric charges seem to be discrete, quantized, small portions. And a large charge is equal to the sum of multiple discrete small portions of charge. That small portion we called elementary electric charge. And after that, we said charges, electric charges are important because they are conserved. Any closed system, any system that doesn't allow charges to go in and out is going to have a constant number of electric charge in it. After that, we started the numerical part of the chapter with Coulomb's law, which describes the strength of force that appears between two point-like charges, separated by a certain distance. And we said, experiment shows that the magnitude of the force between two point-like charges is given with coefficient of proportionality K times the product of the two charges divided by the distance between them squared. So now, this formula is not complete because it only describes the strength, the magnitude of the force, not the direction. We describe the direction with words. We say force is attractive or repulsive. And in order to avoid difficulties, the charges Q1 and Q2 have to be taken in absolute value. So if one of them is negative, the absolute value is going to turn it into positive, and the magnitude of the force by definition is non-negative number, so it's going to work. After that, we said, well, the coefficient of proportionality K has a numerical value of 8.99 times 10 to, I think 10 to the 9th. Let me check my notes because 10 to the 8th or 10 to the 9th. I think it's 10 to the 9th. You need only the order of magnitude of numbers in order to see if a certain situation makes sense. So it is 10 to the 9th. I bet, yes, it is 10 to the 9th. And that constant of proportionality has this numerical value if the space between the 2 point-like charges is filled with vacuum. Filled with air or vacuum. air or empty space, vacuum. We're going to discover later on that it is convenient to represent this constant of proportionality in alternative forms. So the constant of proportionality K should be written traditionally as 1 over 4 pi epsilon naught, where epsilon naught again has numerical value. Well, you can calculate it from this definition, but its numerical value is something like 8.85 times 10 to the negative 12. Appropriate units. So the units are going to be what? For K, the units are Newton times square meter divided by Coulomb squared. And for epsilon naught, the units have to be the inverse of this SI units. Epsilon naught is universal constant of nature, describing electric properties of empty space, of vacuum. And that constant is called electric permittivity of vacuum. Universal constant of nature. If the space between charges is filled with some other medium, water, oil, or something else, the constant of proportionality is different, and different constants of proportionality are tabulated for different materials, and you can find them when they're needed. We're probably not going to need them. Almost only in one chapter we need some electrical properties of different materials, and that chapter is not, it is going to be sometime in the future. Okay, now, after Coulomb's law, we said that historically people tried to switch from interaction from a distance, interaction between charges without direct contact, into a contact interaction. And for that, they used the concept of electric field. So the idea was that the first charge right here creates electric field around itself. And the second charge, if it can, the second charge located here is in direct contact with this electric field and interacts with that electric field, and you see repulsive or attractive forces. Well, later on, people established that this abstract concept of electric field actually is not an invention, but it is real. And the numerical definition for electric field is electric force acting on some charge, positive, call it test charge, divided by the value of that charge. So electric field is force per unit charge. So the electric field in this definition is created by some other charge. And the test charge interacts with this other charge with the force F. Now, since force is a vector, while the charge is a scalar quantity, the electric field E also has to have a vector nature. It is a vector pointing in the same direction as the direction of the electric field, as the direction of the force. Electric field and force. And actually, the electric field in the past, in older textbooks, is referred to as force field sometimes. Now, once you have the concept of electric field as a vector, you have a question how to represent it in geometric form. And last time we said, well, we connect. So this formula tells you that the electric field is an arrow. It is a vector that you attached everywhere in space around the source of electric field. Everywhere in space, an arrow. For the case when the electric field is created by a single point-like charge, it is easy, let's say here it is one positive point-like charge, it is easy to connect those electric field vectors that live everywhere in space with continuous lines, and the resulting map that is filling the space with continuous maps, with continuous lines, is called electric field lines, again called force lines sometimes. So this simple picture in this case that shows the map of the electric field is useful, and you probably have heard about string theory. Some people believe that electric field lines are the simplest representation of fundamental strings. I'm not one of those people, but just to keep you interested in people that are interested in modern physics, this is one way to look at electric field lines, and also to try to understand the meaning of those electric field lines. Now, look, last time we described three properties of electric field lines. They originate from positive or from infinity, and they end up at negative charge or at infinity, right? Like in this case here. The second property was that higher density of electric field lines indicates stronger electric field. And indeed, if you're closer to the charge, the electric field should be stronger, and the density clearly is higher, closer to the charge, at least for the picture on the board. And the last property of electric field lines was that they never intersect. Now, if you combine the definition for electric field, okay, let's call the test charge Q2. If you combine the definition for electric field with Coulomb's law, it follows that the electric field generated by charge Q1 as a source, generated by charge Q1, is going to be given by A times the charge divided by the distance between them, the distance to the point where you want to figure out the electric field squared. So this is one equation that describes the magnitude of the electric field. And again, this equation doesn't give you the direction of that electric field. And usually you either have to describe it with words, or you have to calculate it as you have question or two in the homework assignment, where you have to calculate direction, both direction and magnitude of electric field. So this formula tells you that the closer you get to the source, R becomes smaller, and therefore the result, the electric field closer, is going to be stronger. The closer you're to the source, the stronger the electric field. And you're going to see that actually you have to be careful when the electric fields are not generated by a single point-like charge. This formula is only for electric field generated by a single point-like charge.
Are like super strong electric fields dangerous to humans?
The question is, well, what do you think?
Potentially, probably.
Well, human beings are amazingly delicate things. Actually, any biological organism, maybe with the exception of the COVID virus, is a very delicate thing. So we're going to talk not in much detail about safety when we start talking about electric currents, but in general, yes. So you see that when I charge the Van der Graaf generator, I don't feel like getting closer to it, even though I know that's not going to kill me, it just creates some unpleasant feeling. So you can see your hair goes up and things like that. But in general, if you don't do it very often, it's not going to affect you visibly or in. Well, the things are going to be different when you have electric currents. When this static electric charge starts moving, the situation is going to be different, and we're going to talk about safety when we start talking about electric currents. Yes? No? So, yeah, a strong electric field is not going to kill you until the electric charges start moving. And this is why, well, we're going to talk more about safety when the time comes. Okay, the last section of this chapter is dealing with applications of the concept of electric flux. So our definition for electric flux is always flux through certain area. And electric flux through area A, we defined as a product of the area in square meter, if you want, multiplied by the electric field that is present roughly at the center of this area, multiplied by the cosine of the angle between the normal to the area and the electric field vector. So this is a definition for electric flux that goes through area that is flat, like this piece of paper. And in many cases, for practical applications, you need to define electric flux that goes through some curved surface. And very often, not only curved surface, but whole curved surface. A surface like the surface of a sphere or the surface of a football or some other closed surface. So how to define electric flux through certain curved surface? Well, very simple. You have to break down your curved surface into small pieces, ideally infinitesimally small. So small that each of those pieces can be considered as a flat surface. And after that, calculate the flux that goes through each small flat surface, add the result, and you have the flux that goes through your large curved surface. In other words, the flux that goes through any curved surface is a sum of infinitesimal fluxes through infinitesimal flat pieces. In other words, it is a sum of small area AI times the electric field that goes through the small, infinitesimally small area times cosine of the angle between the normal to this small surface. So you have to make the sum. And people that have done calculus recognize that this type of sum is a Riemann sum, and it can its expression is surface integral. For our purposes, the knowledge of the concept of electric flux through a flat area is sufficient. In one of the homework assignment problems, you're asked to calculate the flux through a certain surface like this. And they give you one angle, but they trick you there by giving you not the angle between the electric field and the normal to the surface, but they give you the angle between the electric field and the surface itself. So don't get tricked. Just apply draw the normal to the area, and from the diagram, from the drawing, you can figure out the value of the angle between the normal and the electric field, and the formula is going to work perfectly fine there. If you encounter that problem, did anybody encounter this problem? Okay, and you didn't get tricked, did you?
I don't think I did, but I also didn't get the right answer, so.
So and now now you know why you didn't get the right answer.
Well,
Luckily, it is a multiple choice problem. You have 10 shots.
Yeah.
And with 10 shots, you should be able to.
Dr. Terry.
Yes.
They said so 90 degrees minus 35 degrees. I think that's minus as it pertains to the homework.
Exactly right. So in the homework assignment, the angle between the electric field vector and the area is given to be 35 degrees. And from there, you can figure out that the angle between the normal and the electric field is 90 minus 35, 65. And cosine of 65 times area times electric field is going to give you the right number for the flux. So, yeah, well, tricky questions are going to appear here and there, and this is why we have classes, and it is your duty to bring those tricky questions in class to discuss them. So keep that in mind for the future. And now, once we have the concept of electric flux defined, we're ready to write the first Maxwell equation called Gauss's law. And Gauss's law is something very simple. Imagine that you have some closed surface, imaginary surface, not real. It could be real, but it doesn't need to be. And it's, of course, it has to be closed surface. In other words, it has to define certain volume. And you may have electric charges here and there, everywhere. You may have electric charge here and here and here and here and here and here. So you can name those electric charges. Let's say Q1, Q2 here, maybe Q3, Q4, Q5. Some of them may be positive, some of them may be negative. Gauss's law says that the electric flux that goes through this imaginary surface is exactly equal to the total electric charge that is inside the volume defined by that surface, divided by a fixed number. Electric permittivity divided by electric permittivity of vacuum. So for our case, Q total is just the algebraic sum of Q3, Q4, and Q5. If you think about only the picture on the board. So Gauss's law, by its mathematical content, is exactly equivalent to Coulomb's law. It doesn't have any other ingredients. It is Coulomb's law written in alternative form. So the question, of course, is to figure out why do we need, instead of using this simple formula that we have encountered the first semester, why do we need the alternative expression? Why do we need Gauss's law the way it is written? Keep in mind that Gauss's law contains this flux concept, which is this infinite sum integral. And so what do you think? Anybody to volunteer an answer? Okay, let me state the question in a different way. What do you think that we write alternative form of Coulomb's law only to confuse students and make their life more difficult, or not? You think so? No? No, come on, be honest. Be honest. You
Maybe a little.
a little? Okay. Well, look, the value of Gauss's law comes from the fact that you have a choice of the shape of this imaginary closed surface. By the way, it's called Gaussian surface. If you choose appropriately the shape of that surface, you're going to be able to calculate electric fields, electric forces in a very, well, maybe not transparent, but easy way. So I'm not going to ask you to do calculations that are too complicated and involve Gauss's law. I'll give you one example now, and a little bit later, you're going to see also that even without calculations, you can predict what the answer is if you have a good grasp of the concept of Gauss's law. Okay, so I'm going to do that in a minute. Before going to that, let me say a few other words about electrical properties of materials. By the way, let's see questions and remarks and comments about what we're just talking here, or anything else. Ashton, how many people are online?
4.
Only 4 people. Yeah.
The shape can be any arbitrary enclosed space, but it has to be enclosed.
It has to be, yes. The surface has to be a closed surface. It has to define a volume in two-dimensional space, yes. Otherwise, yeah, this is a requirement. Now, okay, let's talk. This is another section that I spoke. I talked about insulators and conductors. So all materials around us are roughly divided into either electrical insulators like this plastic, lumber, different plastic materials, rubber, whatever, and electric conductors. In general, electric conductors very often are metals. And we're only going to think about electric conductors as metals. On top of that, we're going to think that those electric conductors are ideal conductors. So currents flow with no resistance to them. Perfect conductors. And by the way, almost all metals are very close to perfect conductors. And if you cool them down sufficiently, you reach a state of superconductivity, at least for some of the metals or alloys, which is zero resistance to moving electric charges. So we're going to treat all metals as if they're superconductors. And metals have, those superconductors, those perfect conductors have almost magical properties. Let's start, well, there are several of those, but let's start with the easy to describe property. So here I can generate some excess charge on this piece of plastic tube, right? Just by rubbing, I can, let's say, generate some excess, let's say, positive charge on the material, on the rubber material. All materials around us in natural condition are electrically neutral. They have the same number of electrons and protons, and their net electric charge is zero. But by rubbing, I can move some electrons from one material to the other, and I end up with electrically charged plastic tube and opposite electric charge to the fabric. For insulators, wherever those electric charges are, they stay there. So if the rubbing is done even in the inside of this material in some way, or I generate those electric charges, wherever they are generated, they are pretty much stuck. They don't move. In the case of metals, electric charges, excess electric charges, only live on the surface of the metal. Nowhere else. They just don't want to stay. The excess charges don't want to stay in the bulk, in the volume of the metal, only on the surface. Well, you can figure out why. I'm not going to comment why at this point. Maybe think about it or read it in the textbook. But this is universal. So in the case of the Van graph, you have this rubber belt that is, let's say, rubbing against some brushes, and eventually excess charges are on the belt. Those excess charges are brought to the metal sphere on top of the Van der Graaf. And even though they're put on the metal from the inside of the sphere, they immediately surface and occupy space on the outer surface of this metal sphere. This is kind of unusual behavior, right? It doesn't need to be that way, but it is. This is what it is. And does anybody have an idea why? Well, you know that like charges repel. They want to get away, as far away from each other as possible. And in the case of metals, they have complete freedom to move with no resistance in the metal, and they can get as far away from each other only if they're on the surface. You can demonstrate that mathematically. So this is one property of the metals. A second property of the metal, of any metal, is that the electric field inside the volume, inside the bulk of the metal, is always zero. This is assuming, of course, that there are no currents flowing through this metal, some piece of wire with current. So this is, again, very strange because you may have very strong electric field. So if I turn on this Van Graph generator, here it is. And if I turn it on and generate and get some excess charges on the metal sphere, the electric field, even relatively at a relatively large distance from the generator, the electric field is going to be strong. And you can even see that the electroscope is feeling it. Even at this distance, the electroscope is reacting to the electric field. If I put more charge, the electric field is going to get even stronger. And the electroscope is going to feel it, even if it is on the other end of the room. Now, if I put this electroscope inside a metal box and close it in a metal box, this electroscope is not going to feel the electric field, no matter how strong the electric field is. Here it is, a metal box. For your convenience, it is made with holes, so you can see what happens. And now look, the electroscope is reacting perfectly fine. But when I put this electroscope here, it is reacting clearly. So I'm losing some charge because I'm touching it with my hands, but it is clearly feeling the electric field. Now, if I put the electroscope inside this piece of metal, the electroscope doesn't feel anything anymore. No electric field penetrates the inside of the metal, even though I have some holes in this piece of metal that make the material a little bit more penetrable by electric fields. Still, even with holes, the electric field is only almost completely neutralized. So, in other words, this piece of metal divides the universe into two parts. An observer inside this part of the universe doesn't know about anything electrical in this part of the universe. So this is a very strange property. This is very unexpected. And of course, it has practical applications. So in any electronic device where you have to protect sensitive electronic chips from external fields, you place them, you surround them usually with aluminum casing, so that external fields never get inside this aluminum encasing. Also, talking about safety, in a thunderstorm, if you are inside your car, you're pretty much safe. No matter how many lightnings are hitting around you or hitting the car, if you're inside the car, you're fine. Even though the car is, again, not a perfect enclosure, it has windows, at least most cars have windows. But while you're inside, no electric phenomena can penetrate the inside of the metal enclosure. So again, think about it. This device, by the way, is called Faraday's cage. Whatever is inside the cage is completely protected from electric fields. So this is a second. This is one second property of the metals. Electric field inside the bulk of the metal is zero. Always. Well, except when current is flowing in that metal, then the things change. And the last properties of metals is that electric field lines, let's say from anywhere, are always perpendicular to the surface of the metal. So electric field lines may be created by this Van der Graaf, or it may be the electric field lines due to some charge that is on this piece of metal. It doesn't matter where the charge is. Electric field lines are always perpendicular to the metal surface, locally, perpendicular to the surface. This is useful actually, as you're going to see in a minute, well, it practically defines. So look, the electric field lines are, if there is no metal and only this Van der Graaf is in this room, the electric field lines are in radial direction, away from the metal, from the Van der Graaf, from the sphere. If I put a metal there, the electric field lines start bending in such a way they to be perpendicular to every single spot on this piece of metal. Okay, any remarks so far? Okay, now let's consider, let's try to figure out what is the electric field created by a very large flat piece of metal with some net charge. So here is a very large piece of metal. I actually have one right here. Some, I guess, some aluminum alloy. Imagine that this is very large compared with the distances in this room. And imagine that I take some charge from the generator and place it in the metal. Because of the symmetry of this piece of metal, this excess charge is going to be uniformly distributed on the surfaces of this piece of metal. Well, the only large surfaces, the small surfaces on the sides don't matter that much. So the question for us is, if I have a total charge, excess charge Q that I place on the surface of this fat piece of metal, what is going to be the electric field at certain place, let's say somewhere here, at distance of 20 centimeters or so from this very large piece of metal. And well, the first step is to realize that the excess charge Q is going to be uniformly distributed on the surfaces. So in other words, we say that the electric charge has uniform surface density sigma, which you calculate as total charge divided by the area. So this is certain amount of uniformly distributed surface charge on the piece of metal. Now, the only way you can calculate easily the electric field, here is your piece of metal right here. The only way you can easily calculate the electric field at this point is to use Gauss's law, the only easy way. Gauss's law written in this form. And we have 2 more minutes. Let me just describe how you do it. So what you do is, first, you realize that the electric field, if this charge is positive electric charge on the surface of the metal, and we said that the symmetry requires it to be uniformly distributed, the electric field lines are going to be perpendicular to this metal surface. So here are the electric field lines. Next, imagine a closed surface with the shape of a box. So here is a closed surface with the shape of a box, in a way oriented, this imaginary surface, oriented in a way that is shown on the board. Well, because the electric field lines are the way they are drawn, the electric flux through this imaginary surface is going to be non-zero only through this part of this side of the box, and also from this side of the box. The electric field lines are skimming through the lid, therefore no electric flux through this side. The electric field lines are skimming also through the bottom, through the base of the box, zero flux there too. Also, this side also is parallel to the electric field lines. Again, you have zero flux there. The only sides that have non-zero electric flux going through those sides is this one and this one. Well, make this A prime, and let's say that this side is A, and this side is also A. The total flux that goes through those two flat surfaces, imaginary surfaces, is going to be the area times the electric field, whatever it is, at this distance from the source. Cosine of the angle is going to be 0 degree. Angle between the normal to the surface and the electric field is 0. Cosine of 0 is 1. I'm not going to write it. So this is the flux through one of the flat imaginary sides, and the same flux through the other one. So the total flux is twice that. And that total flux has to be the total charge inside the box divided by this fixed number. But the total charge inside the box is equal to surface charge density times area, all of this divided by epsilon naught. Now, here is the equation. The area cancels out, and you get that the electric field at this position away from your flat charged piece of metal is equal to sigma divided by 2 times epsilon naught. Very surprising result, because it tells you that no matter how far you go from the source, the electric field strength doesn't drop. It is surprising, but look, it is not that surprising, because we assume that this charged piece of metal is infinitely large. So when you work with infinities, everything can happen. So next time we're going to say, I'm going to write next time, what would be the electric field between two oppositely charged pieces of metal, flat pieces of metal, like here. And this is going to be our first encounter of a device that is called capacitor. So we're going to continue on Wednesday. Let's see questions and remarks. The homework assignment is due next week on Wednesday. So don't feel rushed for time. So on Wednesday, I'm going to solve any problem that you ask to be solved. And on Wednesday, I'm also going to have a quiz on the screen. And you have to answer the questions on this quiz by raising your hand. And by Wednesday, we're going to have also the brownie point file where you can enter your brownie points. So see you next week on Wednesday, and have a nice weekend.
So I'm good to just end it and it sends the link to you and everything.
End it, no problem at all. It is going to send me the email.